Our lesson today is on conditional probability and independence. The probability we assign to an event can change if we know that some other event has occurred. This idea is the key to many applications of probability. When we're trying to find a probability that one event will happen under a condition that some other event is already known to have occurred, we are finding what's called a conditional probability. So we define a conditional probability as the probability that one event happens given that another event is already known to have happened. Suppose we know that event A has happened, then probability that event B happens given that event A has happened is denoted by probability of B given A, and it looks like a simple little line segment as the symbol. The order matters with conditional probabilities. We have to look at, is it B given A or A given B? We read that symbol then as given that or under the condition that. Consider a two-way table. Define the events E. The grade comes from an EPS course, and L, the grade is lower than a B. So here are some probabilities. Totals are calculated. Probability of L, so that would be below a B, is 3656 out of 10,000. We give it as a fraction and as a decimal. Probability of E given L would be 800 out of 3656. And probability of L given E, so probability the grade is lower than a B given the grade comes from an EPS course, would be 800 out of 1,600. If we know a person owns a home, what's the probability the person is a high school graduate? There are a total of 340 people in the sample that own a home. So because there are 221 high school graduates among the 340 homeowners, the desired probability is 221 out of 340, or 65%, 0.65. If we know a person is a high school graduate, what is the probability the person owns a home? There are a total of 310 people who are high school graduates. That's right here. And because there are 221 homeowners among the 310 high school graduates, the probability would be 221 out of 310, 0.71 or 71%. So the 221 and 310. If we know that one event has happened does not change the likelihood of another event, we say the two events are independent. Two events, A and B, then are defined as independent if the occurrence of one event has no effect on the chance the other event will happen. In other words, events A and B are independent if the probability of A given B is equal to the probability of A, and the probability of B given A equals the probability of B, or the probability of A given B equals the probability of A not given B. Remember, complement is like saying 1 minus that, or it's not that. Here's the big deal. With these, you have to make sure that the numbers match. If the numbers are equal, they're independent. If the numbers are not equal, they're not independent. Use mathematics to figure out your answers. So here's an example. Are the events male and left-handed independent? Probability someone is left-handed, given that they're male, would be 3 out of 23.13. The probability somebody is left-handed would be 7 out of 50. The probabilities are not equal, therefore the events male and left-handed are not independent events. The event of interest in our scenario earlier of who owns a home was probability of A is a high school graduate, B owns a home. We've already learned that probability of B is 0.68 or 68%, and the probability of B given A is 221 out of 310, or 71.2%. We know the randomly selected member of the sample has a 68% probability of owning a home, but we know the randomly selected member is a high school graduate, and the probability of owning a home then increases to 71.2%. So they are not independent if they are not equal. So here's a question: is there a relationship between gender and having allergies? To find out, we use a random sampler at the United States Census at school website to randomly select 40 U.S. high school students who completed a survey. The 2A table shows the gender of each student and whether the student has allergies. Are the events female and allergies independent? So to check if the two events are independent, we would check to see if knowing a student's gender affects the probability that the student has allergies. We know how to describe a sample space. Another way to model chance behavior is to use a tree diagram. Consider flipping a coin twice. What is the probability of getting two heads? Here's our sample space that we would write out. Probability of two heads is 1 out of 4. Here is the sample space of the choices. Here's what it would look like in a tree diagram. We have a coin toss. The probability of tossing a coin for the coin toss is a half. For a head, each time it's a half. So the probability of getting two heads is a half times a half, or 1/4. Here's another example. Back to the idea of the allergy. Suppose we chose two students at random. Draw a tree diagram that shows the sample space. So here's what this would look like on a tree diagram. So we randomly select a student. We have 18 out of 40 that have allergies, and then from the first student, and then 17 out of 39, that would be that's our 17 right here, and then that's for the second student, and then the next one we'd have 22 out of 39 that are not. Then we have 22 out of 40. This is for does not have allergies and no allergies. For the next one, we'd have 18 out of 39. And then here we'd have 21 out of 39. So to get two students who suffer from allergies, we need to get an allergy sufferer for the first student and an allergy sufferer for the second student. So following along the tree, we see the probability of two allergy sufferers is the probability the first student has allergies and the second student has allergies. So we multiply probability the first student has allergies and the probability the second student has allergies given the first student has allergies. So that would be 18 out of 40 and then 17 out of 39. There's a 20%, so 0.196 is a 20% chance of selecting two students with allergies. The idea of multiplying leads to a general probability rule of P intersect B, that two events happen together. So here's the general multiplication rule for probability. The probability that events A and B both occur can be found using the general multiplication rule. Probability of A intersect B is probability of A times the probability of B given A, where probability of B given A is the conditional probability event B occurs given event A has already occurred. Here's a note. The rule is not on the formula sheet for the AP exam. However, it is the conditional probability formula just rearranged, which is on the formula sheet. Here's an example. What percent of teens are online and have posted a profile? So here's our probability tree diagram. We have 93% of the teenagers use the internet. 55% of online teens have posted a profile on a social networking site. So we have 0.93. So online, here's the question. Yes, we have 55% who did. That would leave 45% who would not. And that would leave 7% of teenagers that do not use the internet. And then we would have, of course, not use the internet, and posting a profile makes no sense, so there's zero probability. And then not using the internet and not posting the internet site, we would have a probability of 1 in this case, or 100%, because they've not used the internet. So here's the outline. Probability of online is the 0.93. Probability of a profile given an outline, that's the second tier, is 0.55. So probability of profile, that's this part right here again, given that they're a yes to the online. So we multiply 0.93 times 0.55 and get 0.5115, which means 51.15% of teens are online and have posted a profile. Another example, 55% of high school students participate in a school athletic team at some level, and about 5% of the athletes go on to play on a college level team in the NCAA. What percent of high school students play a sport in high school and go to play in the NCAA? We know probability of high school sport is 0.55, and probability NCAA sport given a high school sport is 0.05. So we have probability of high school sport and NCAA sport. We multiply the numbers. 0.55 times 0.05 is 0.0275. So about 3% of high school students will actually play a sport in high school and in the NCAA. What percent of all adult internet users visit video sharing sites? So here's a tree diagram, and here's some results. The probability of video yes and the age group, we multiply those numbers together. So 0.27 times 0.7, that's this tier right here. Probability of video yes and 30 to 49 is 0.45 times 0.51, and probability of video yes intersect age 50 and up is 0.28 times 0.26. So probability of video yes, we add these probabilities together. So it would be all three of the numbers added together to get our total probability. We're adding these three numbers together. Light user, we look at the percentages. It's 0.17, probability of a moderate user, 0.62, so these are people that use media, and then heavy user is 0.21. So the probability of good grades given the probability the person is a light user is 0.74. Good grades given moderate user is 0.68, and good grades given a heavy user is 0.52. So this is all from the data, the percentages. We want to find the unconditional probability. So if we choose a subject in the study at random, and we want to find the unconditional probability, where the tree diagram was on the previous slide, we can add the probabilities of being in one of the three groups. So we have to multiply the numbers together first of each of those combinations, and then add them all together when we're done. When A and B are independent, we can simplify our general multiplication rule. So for multiplication rule, independent events, the probability of A and B both occur. So probability of A and B is probability of A times the probability of B. Example, following the Space Shuttle Challenger disaster, it was determined the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated the probability an individual O-ring joint would function properly was 0.977. Assuming O-ring joints succeed or fail independently, what's the probability all 6 would function properly? So the probability of joint 1, okay, and 2, and 3, and so on up to 6. We would multiply the probabilities together and get 0.87, or 87%. Here's another example. In a baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning where no hitters reach base about 40% of the time. What is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance is independent of his performance in other innings? The probability of having 9 perfect innings, we'd multiply these together, so it's the same as saying 0.4 times 9, so 0.00026, which would mean 1.3 perfect games per season, with 30 teams playing 162 games per season. Here's another example. Hacienda Heights and La Puente are two neighboring suburbs in the Los Angeles area. According to the local newspaper, there's a 50% chance of rain tomorrow in Hacienda Heights and a 50% chance of rain in La Puente. Does this mean there is a 0.5 times 0.5 equals 0.25 probability? The answer is no. It is not appropriate to multiply the two probabilities because they aren't independent events. If it's raining in one of the locations, there's a very high probability it is raining in the other. However, suppose there were also a 50% chance of rain in New York tomorrow. To find the probability it will rain in Hacienda Heights and New York, it would be appropriate to multiply, since it is reasonable to believe the weather in Hacienda Heights is independent of the weather in New York. So here's an example of two events being independent and two events being mutually exclusive. Select a card from a standard deck and define. Event A is the probability is the card is red. Event B, the card is a club. Since there are no red clubs, A and B are mutually exclusive. But since the probability of A is 0.5 and the probability of A given B is 0, the events are not independent. Remember, independent means that the numbers have to match up. So here's event A, the card is red. This time, event B, the card is a 7. Since there are red 7s, A and B are not mutually exclusive. But since the probability of A and the probability of B equal 0.5, these are independent as well, as being not mutually exclusive. The next one, event A, the card is red. Event B, the card is a heart. All the reds are hearts are red. A and B are not mutually exclusive, and the probability of A, the card is red, is 0.5. Probability of A given B is 1, so they are not independent. So this is to try to help you to see the difference between mutually exclusive and independent. If we rearrange the terms in the multiplication rule, we get a conditional probability formula. Here's what it looks like. The probability of B given A is the probability of A intersect B over the probability of A. Probability both events occur, probability given event the event occurs. What is the probability a randomly selected resident who reads USA Today also reads the New York Times? Probability of B given A. Here's the math. The intersection is 0.055%. The probability of A was 40%. That's the whole circle. We divide 0.05 by 0.4 and get 0.125. So 12.5% chance a randomly selected resident who reads USA Today also reads the New York Times. Another example. What is the probability a randomly selected household with a landline also has a cell phone? So probability of cell phone given a landline, probability of cell phone and landline over probability of a landline. So that would be 0.60 divided by 0.78. So 0.77 or 77% chance that a person with a landline phone also has a cell phone. Here's an early example with grades. What percent of youth with good grades are heavy users of media? So we find the probability of a heavy user and good grades, which was 0.1092 that we calculated from earlier, over the probability of the events of good grade, which was the adding of the numbers together. You can also get this number, by the way. It's right here in the multiplication of these two numbers on the chart or the tree diagram. So here's one more example. What is the percent of people who test positive actually use illegal drugs? So we follow the tree diagram. Probability of took drugs and tested positive, or probability of tested positive. So probability that they took drugs and tested positive is 0.036, and then probability tested positive, we'd add these two under the test result of positive together, and we divide these out, we get 0.429 or 42.9%. We have several formulas to make sure to look over the formulas and versus taking a look at the terminology, tree diagrams, and make sure that you understand the different ways to solve